For over 50 years, one question has hung over the Sea of Tranquility. The place where humans first touched another world, what does it look like today? The lander, the flag, the footprints, are they still there? For decades, the answer seemed obvious. Point a telescope at the moon and look. People assumed we could. They were wrong. Every telescope on Earth, even Hubble, sees the same thing at that spot. Nothing. A blank point of grey. And yet, we now know exactly what the site looks like, because one camera finally photographed it. And what it revealed was stranger than anyone expected. A flag that is no longer standing, trails of footprints you can trace from space, and one instrument, still working after half a century, whose signal has become 100 times weaker than it should be. Something up there is slowly changing the place we left behind. So, let's take a look. Back in the early 2000s, an astronomer named Phil Plait found himself arguing with strangers almost every week. The same argument, over and over, with people who believed the Apollo moon landings were faked. And these people had what they thought was their ace in the hole, a single question they believed no scientist could answer. If the Hubble Space Telescope is powerful enough to photograph the intricate details of galaxies billions of light years away, why can't it show us the astronauts' boot prints on our own moon? It sounds devastating. It feels like a checkmate. It isn't. Like most conspiratorial thinking, the argument seems persuasive on its surface and then falls apart under the slightest scrutiny. But here's the thing. Falling apart under scrutiny is not the same as being a stupid question. The question itself is actually a very good one. The people asking it were simply wrong about two things: how telescopes really work and just how big space really is. Now, the facts of the landing are not in question. On July 20th, 1969, Neil Armstrong and Buzz Aldrin set the lunar module Eagle down in the Sea of Tranquility and spent 22 hours on the surface. They planted a flag. They set out scientific instruments. They left boot prints in the dust. And then they climbed back into the top half of their spacecraft and flew away, leaving the descent stage of the Eagle sitting on the moon, the largest single artifact of humanity's first visit to another world. At some point during that stay, one of them, probably Aldrin, turned around and photographed the lunar module, with the Earth hanging almost directly overhead. That was more than half a century ago. Nobody has stood there since. So what does that place look like today? The flag, the footprints, the machine they left behind, what happened to them after 50 years alone on the moon? The obvious answer is to look. We have giant telescopes on mountaintops. We have Hubble floating above the atmosphere. Surely one of them can just check. But here's the weird part. They can't. Not Hubble. Not the largest telescopes on Earth. Not any telescope humanity has ever built. And the reason why reveals something surprising about the limits of what we're able to see. Most people think a telescope's job is to magnify things. Manufacturers of cheap telescopes love this idea. They print it in huge letters on the box. 150 times power. But magnification is not what makes a telescope powerful. The real strength of a telescope is something called resolution. And the difference between the two is subtle, but it changes everything. Magnification just means zooming in, making a thing look bigger. Resolution is the ability to distinguish two objects that are very close together to actually separate the details. Here's an easy way to feel the difference. Take a photograph on your phone and zoom in. Keep zooming. Past a certain point, you're not seeing new detail anymore. You're just magnifying the pixels. The information simply is not there, and no amount of zoom will create it. To break through that wall, you don't need more magnification. You need more resolution. And resolution runs into a wall of its own, a wall built into the nature of light itself. When light from a distant point, say, a star, passes through a telescope, it spreads out a little inside the optics. This is a fundamental property of light called diffraction, and it cannot be avoided, not with better engineering, not with cleaner mirrors. It is simply what light does. The only way to fight diffraction is to build a bigger mirror. The bigger the light-gathering optics, the finer the detail you can resolve. Which brings us to Hubble. The Hubble Space Telescope is roughly the size of a bus. About 13 meters long, 4 meters across, weighing around 11 tons, circling the Earth at 28,000 kilometers per hour, completing an orbit every 96 minutes. Its mirror is 2.4 meters wide, and at its very best, that mirror gives Hubble a resolution of about 5/100ths of a single arc-second. Now, an arc-second is a very small slice of the sky. There are 90 degrees from the horizon straight up to the zenith. Each degree splits into 60 arc-minutes. Each arc-minute splits into 60 arc-seconds. The entire full moon, the whole glowing disk you see at night, spans about 1,800 arc-seconds. And Hubble can resolve 1/20th of one of those seconds. That is equivalent to making out a dime from about 140 kilometers away. Now, that precision did not come easily. When Hubble launched in 1990, its main mirror carried a hidden flaw. A faulty measuring device used during the polishing process had left the mirror 2 microns too flat, an error smaller than the width of a human hair and enough to blur the vision of the most expensive telescope ever built. For its first 3 years, Hubble was nearsighted. Astronauts eventually flew up and installed a corrective optical device called COSTAR, a series of curved mirrors that fixed the light path, essentially giving the telescope glasses. In later servicing missions, every instrument was replaced with versions that had the correction built in, and COSTAR itself was removed in 2010. The flaw is still in the mirror to this day. It's just perfectly compensated for. The point is, this telescope has been polished, corrected, serviced, and upgraded across 5 missions until its optics became essentially perfect. It has made over 1 million observations. Whatever Hubble cannot see, it is not because of a defect, it is because of physics. That sounds unbeatable. So what's the problem? The problem is that resolution is an angle, not a size. How much real detail you see depends entirely on how far away the target is. Galaxies are typically tens of millions, even billions of light years from Earth. At those distances, Hubble's incredibly sharp vision still can't make out anything smaller than a few light years across tens of trillions of kilometers. So when you look at those spectacular Hubble images and feel like you're seeing galaxies in fine detail, the smallest thing in that picture is still tremendously, incomprehensibly huge. The moon is different. The moon is close, only about 380,000 kilometers away. And this is where we hit the single most surprising fact in this entire story. At the distance of the moon, Hubble's resolution limits it to seeing objects no smaller than about 90 meters across. 90 meters, the size of a football field. Sit with that for a moment. The telescope that has photographed galaxies whose light traveled more than 13 billion years to reach us cannot see anything on our own. Moon smaller than a stadium. The Apollo lunar landers are about 4 meters across. To Hubble, the entire Apollo 11 landing site, the lander, the flag, the instruments, every footprint is more than 20 times smaller than the smallest thing it can possibly detect. It all vanishes into a single point of gray. Hubble has, in fact, been pointed at the moon a few times. It has to be done with the greatest care, because the moon is very bright, and its normally avoided Hubble orbits the Earth so quickly that the moon appears to swing back and forth across its view, and the telescope can barely compensate. It once photographed the region where Apollo 17 landed, the Taurus-Littrow Valley. The image shows the valley. It shows the mountains. It shows no sign whatsoever of the lander or anything the astronauts did there. And before you ask about Hubble's famous successor, the James Webb Space Telescope doesn't solve this either. Yes, its mirror is 6.5 meters across, much bigger than Hubble's. But there's a catch. Resolution doesn't depend only on the size of the mirror. It also depends on the wavelength of the light, and shorter wavelengths give sharper vision. Webb was designed as an infrared telescope, observing long wavelengths that let it peer through cosmic dust and back toward the early universe. At those wavelengths, around 2 microns, its resolution is merely comparable to what Hubble achieves in visible light. Further out into the mid-infrared, its resolution is even lower. Webb is the sharpest infrared eye humanity has ever launched, and it still cannot see a lunar lander. So, could we just build a bigger telescope? Let's run the numbers the way physicists have. The lunar landers are a little over 4 meters across, sitting roughly 384 million meters away. One physicist put it this way: that makes them about as hard to see as a single coin from 1,000 miles away. To detect a lander from Earth as even a single pixel of light, you would need a telescope with a mirror at least 200 meters across. The largest visible light telescopes on Earth are about 10 meters. And if you wanted the lander to appear as more than 1 pixel, an actual picture, with shape and detail, you would need a mirror a few miles wide. And even that wouldn't be enough, because every telescope on Earth sits at the bottom of an ocean of air. In exactly the same way the surface of water scatters light, our atmosphere blurs everything astronomers try to see. We can fight back some observatories, fire lasers into the sky to measure the shimmer of the air and correct for it, but our techniques aren't perfect. There is one more twist worth knowing. Astronomers have asked what Hubble could squeeze out under absolutely perfect conditions, observing in ultraviolet light, where its resolution is sharpest, and then applying aggressive image processing. The answer? Objects on the Moon about 40 meters across. Better. Still 10 times too coarse to see a lander. So this is not a failure of engineering. Hubble's optics are essentially perfect. The roadblock is more fundamental. It is the physics of light itself telling us, from here, you will never see it. Which leaves only one option. If the telescope cannot come to the mountain, the telescope has to go to the Moon. On June 18th, 2009, NASA launched a robotic spacecraft called the Lunar Reconnaissance Orbiter. Its mission: to map the surface of the Moon in more detail than ever before. 5 days later, on June 23rd, it began sending back images, and it was carrying a camera with a mirror only about 20 centimeters wide. Now, think about that. 20 centimeters. Hubble's mirror is 2.4 meters more than 10 times wider. By everything we just learned about resolution, this little camera should be hopelessly outclassed. But resolution is an angle. And angles don't care how big your mirror is if you simply move closer. The Lunar Reconnaissance Orbiter wasn't looking at the Moon from 380,000 kilometers away. It was in orbit around the Moon itself, eventually passing over the surface at an altitude of just 50 kilometers. That is why we send probes to other worlds. From up close, a modest camera beats a giant telescope every time. Sometimes there is no substitute for being there. And then, in July of 2009, between July 11th and July 15th, while the spacecraft was still maneuvering down toward its final orbit, the Lunar Reconnaissance Orbiter passed over the Sea of Tranquility. 40 years, almost to the day, after Neil Armstrong and Buzz Aldrin landed there, its camera captured a small, dark, angular speck casting a long shadow across the lunar plain. The descent stage of the Eagle, exactly where they left it. For 4 decades, the site of humanity's first footsteps on another world had been unseeable, a place we knew existed, that no living eye could check on. And now, suddenly, there it was, a real object, in a real photograph, sitting quietly in the dust. And the orbiter was just getting started. That first image was taken before the spacecraft had even reached its mapping altitude. Once settled into its near-surface orbit, its camera could resolve details on the Moon down to about half a meter, roughly twice as sharp as that first look. Later, imaging the site from a height of just 24 kilometers, the orbiter captured something that stops you cold. You can see the paths around the descent stage, thin, dark, meandering trails wind through the gray. They lead from the lander to a scientific instrument called the Passive Seismic Experiment, to another called the Lunar Ranging Retroreflector, and one trail wanders east, out to the rim of a small pit called Little West Crater, the short exploratory walk Armstrong made near the end of the moonwalk. Those dark lines are the astronauts' boot prints. Not individual prints. Even from 24 kilometers up, a single boot print is too small to resolve. What the camera sees is the trail itself, the darkened track of soil disturbed by two humans walking, 57 years ago now, preserved so perfectly that you can retrace every route they took during their 22 hours on the surface. The orbiter went on to photograph every Apollo landing site. At the Apollo 17 site, you can see something even stranger: long, meandering lines crossing kilometers of terrain, tracks left by the wheels of the lunar rover, looking as if they were made yesterday. So the question is no longer whether the hardware is there. We can see it. The question becomes something deeper. Why does it all still look untouched? And is it really as untouched as it looks? On Earth, a footprint on a beach lasts until the next wave. A footprint in dust lasts until the next gust of wind. Erosion is so constant here that we barely think of it as a process at all. It's just what happens. The moon plays by different rules. There is no air on the moon, no wind, no water, no rain has ever fallen there. None of the machinery that erases marks on Earth exists there at all. So when a boot presses into the lunar surface, the print it leaves has, in a sense, nothing to fear. And the surface itself is stranger than it looks. That grey powder coating the moon is called regolith, a layer of crushed rock covering essentially the entire lunar surface, in most places several meters deep. It wasn't made by weather, it was made by violence. For billions of years, meteoroids and micrometeoroids have been slamming into the moon at speeds of tens of kilometers per second, with nothing to slow them down, grinding the bedrock into progressively finer material. That gives lunar dust a property Earth dust doesn't have. Dust on Earth gets tumbled by wind and water until its edges are rounded smooth. Lunar dust is never tumbled. Its particles stay sharp, jagged, angular, glassy fragments that catch and interlock against each other. The astronauts discovered that this dust clings to everything it touches. It worked its way into their suits, and when they got back inside and took their helmets off, they reported that it smelled like spent gunpowder. Those sharp, interlocking grains are why a boot print on the moon holds its shape so crisply. And it's why, packed and compressed just below the surface, the ground becomes remarkably firm. We actually have direct evidence of how long such marks survive. In April of 1967, a robotic lander called Surveyor touched down on the moon and photographed the imprint its own landing pads had pressed into the regolith, a neat waffle pattern from the footpad's underside. 31 months later, the astronauts of Apollo 12 landed nearby, walked over to the old robot, and photographed that same footprint. It was still there, clearly visible, apparently completely unmodified, 31 months and not a grain out of place. So the simple picture is this. The Apollo 11 site is a place where time, in the everyday sense, has stopped. The boot prints, the equipment, the discarded gear, all of it frozen in the moment the ascent engine fired. That picture is mostly true. Mostly. Because the moon does have one agent of change, we've already met the same bombardment that made the regolith in the first place, continues today, endlessly gardening the surface one microscopic impact at a time, on timescales of millions of years. And it has another one, a much quieter one that scientists are still working to understand. Because it turns out the dust on the moon does not always stay on the ground. Hold that thought. We'll come back to it. First, we need to talk about the flag. Of everything left at Tranquility Base, one object gets asked about more than all the others combined. Is the American flag still standing? The story of that flag is stranger than most people know. It almost wasn't an American flag at all. In January 1969, President Richard Nixon used his inaugural address to frame space exploration as a shared human adventure, new worlds to be explored together, not conquered. That inspired an idea inside NASA. Perhaps the first landing should plant the flag of the United Nations. A committee was formed to decide, and it faced a genuine legal puzzle. The Outer Space Treaty of 1967 prohibits territorial claims to any celestial body. Would planting a national flag look like the old colonial gesture of taking possession? The committee surveyed officials, canvassed the public, and consulted institutions from the Smithsonian to the Library of Congress. The overwhelming answer came back: plant the American flag, but make unmistakably clear it claims nothing. So, alongside the flag, a plaque was fixed to the descent stage of the lunar module, the part that stays behind forever, reading, "Here, men from the planet Earth first set foot upon the moon. July 1969. AD, we came in peace for all mankind." Months after the landing, Congress passed a law stating plainly that the flag was a symbolic gesture of national pride, not a declaration of sovereignty. That plaque, by the way, is still bolted to the Eagle's descent stage in the Sea of Tranquility, right now the quiet fine print of humanity's first visit. But someone still had to figure out how to make a flag fly where there is no air. And that job landed on the desk of a NASA engineer named Jack Kinsler about 3 months before launch. Kinsler was the head of technical services at the Manned Spacecraft Center in Houston. His colleagues called him Mr. Fix-It. The problem sounds trivial and isn't. A flag on the moon hangs in nothing. There is no wind. An ordinary flag on an ordinary pole would simply droop against the staff like a wet towel, and every photograph of humanity's proudest moment would feature a sad ribbon of limp fabric. Kinsler's solution came from childhood. He remembered his mother hanging curtains, sliding a rod through a hemmed pocket sewn along the top of the fabric. So that's what he designed. A horizontal crossbar threaded through a hem sewn into the top of the flag, holding it permanently outstretched. On the airless moon, it would appear to fly forever. The flag itself was nothing special, and that detail matters enormously for what comes later. It was an ordinary nylon flag, 3 feet by 5 feet, ordered from a government supply catalog. It cost $5.50. The telescoping poles, gold anodized aluminum tubes, cost about $75. The whole assembly had to work within the reach of an astronaut in a stiff pressurized suit no lower than 28 inches, no higher than 66. Getting it to the moon intact was its own engineering problem. The flag rode to the surface, strapped to the ladder of the lunar module, directly in the path of the descent engine's exhaust, where temperatures during the final 13 seconds of landing were calculated to reach 2,000 degrees Fahrenheit. So, the $5 flag was sealed inside a protective case of stainless steel, aluminum, and layered insulation that kept it below 180 degrees. On the surface, Armstrong and Aldrin ran into trouble almost immediately. They tried to drive the pole into the ground and couldn't. Those same sharp, interlocking dust grains that preserve footprints so beautifully also locked together against anything pushed into them. The two men managed to sink the pole about 7 inches deep. When they stepped back, it stood but only just, and it was standing roughly 27 feet from the center of the lunar module. That distance turned out to matter, because when the mission ended and the ascent stage fired its engine to leave the moon, Buzz Aldrin, looking out the window, saw the blast of the rocket exhaust knock the flag over. For decades, that was simply Aldrin's recollection, one man's glimpse through a small window during the most intense ride of his life. There was no way to check, no telescope could see it. The question just sat there, unanswered, for 43 years. Then, in 2012, researchers reviewed Lunar Reconnaissance Orbiter photographs of the Apollo sites, and the images held a quiet surprise. At the Apollo 12 site, the Apollo 16 site, and the Apollo 17 site, the flags are still standing. The poles themselves are too thin to see, but as the sun moves across the lunar sky, the images show shadows sweeping around a fixed point, shadows cast by flag fabric that has not disintegrated. And at the Apollo 11 site, nothing. No flag, no shadow. Aldrin was almost certainly right. The first flag planted on the moon likely stood for a matter of hours, and has spent the last half-century lying in the dust where its own spacecraft knocked it down. But here's where the story turns quietly haunting. Those flags that are still standing, they are almost certainly no longer flags in any meaningful sense. Remember, $5.50 from a government catalog, never designed for space, and the lunar environment is merciless to fabric. A day on the moon lasts about 27 Earth days, which means every flag endures roughly 2 straight weeks of searing, unfiltered sunlight and heat around 100 degrees Celsius, followed by 2 weeks of darkness at around 150 degrees below zero, over and over, for more than 50 years. On Earth, the atmosphere absorbs some of the sun's ultraviolet radiation, and even so, a flag flown in bright sunlight fades within years. On the moon, there is no atmosphere, and outside of craters, no shade. Experts who have studied the problem believe the flag's colors have long since been bleached away entirely, that the stars and stripes are now blank, bone-white sheets. Some of the fabric may have physically disintegrated under the ultraviolet flux. So this is what the orbiter's photographs cannot quite tell you, and what the physics fills in. Somewhere in the Sea of Tranquility lies a white flag, face down in the dust. Not a symbol of surrender, just the honest result of hanging a $5 piece of nylon in the harshest environment humans have ever visited. Now we can return to the mystery from the beginning, the laser and the missing light. Among the equipment Armstrong and Aldrin carried onto the surface was a suitcase-sized panel studded with 100 small glass prisms called corner cubes. Each one has a remarkable property. Any beam of light that enters it is reflected back exactly the way it came. Not scattered, not deflected, returned, precisely, to its source. It was called the Lunar Ranging Retroreflector. The team that built it designed, tested, and delivered it within 6 months of receiving the contract. The astronauts set it on the regolith, aimed it at Earth, and left. It needs no power. It has no moving parts. It cannot break in any ordinary sense. And that makes it the only Apollo 11 experiment still operating today. Here's how it works. An observatory on Earth fires a laser pulse at the reflector's location. The pulse crosses the gulf between the worlds, strikes the corner cubes, and bounces straight back. By timing the round trip, scientists measure the distance between the Earth and the Moon down to astonishing precision. The very first laser echoes came back in 1969, tracked for years by the 7-meter telescope at McDonald Observatory in Texas using a ruby laser. Apollo 14 and Apollo 15 added reflectors of their own, and 2 Soviet robotic rovers, Lunokhod 1 and Lunokhod 2, carried reflectors as well, one of which was actually lost and then rediscovered by laser, ranging in 2010. In 1984, observatories in France and Hawaii joined in. And over more than 4 decades, this quiet experiment has produced around 17,000 precision measurements of the moon's distance. What has all that ranging told us? An enormous amount. It refined our knowledge of the moon's orbit, its physics, its interior, and it became one of the strongest tools ever devised for testing Einstein's theory of general relativity. Decade after decade, measurement after measurement, the theory has been checked against the moon itself. No violations have ever been found. Then, in 2006, a new station came online, the Apache Point Observatory Lunar Laser Ranging Operation in New Mexico, using a 5-meter telescope designed to measure the Earth-Moon distance to the precision of a single millimeter. Its return signal rates were about 70 times higher than the best ever achieved before. And with that sensitivity, it could do something no station had managed in about 20 years, range to the reflectors even during the full moon. That's when the anomaly appeared. The reflectors are dimming. Careful analysis of the returning signal shows that the efficiency of the 3 Apollo reflector arrays is now diminished by a factor of 10 at all lunar phases. The light coming back is 1/10 of what it should be. And here's the weird part. When the moon is full, when the sun shines face-on into the corner cubes, the signal drops by an additional factor of 10, 100 times weaker. These deficits did not exist in the earliest years of lunar ranging. The data shows the degradation began within roughly a decade of the reflectors being placed on the surface. Something in the lunar environment has been slowly attacking the only working machines we left behind. What could it be? The leading suspects bring us back to that quiet agent of change we set aside earlier. Dust or fine abrasion on the front faces of the corner cube prisms. A thin contamination would dim the reflections at all times, and at full moon, dust sitting on the glass would absorb the direct sunlight, heating the prisms unevenly and distorting their optical performance. Tellingly, during lunar eclipses when the Earth briefly blocks the sun, observations suggest that full moon deficit abates. But this raises a question that should bother you. There is no wind on the moon, nothing to blow dust around. The reflectors sit on flat, undisturbed ground. So how does dust get onto a panel of glass a meter above the surface? The honest answer is, we are not entirely sure. But the moon has been dropping hints for a long time. In the 1960s, several of the robotic surveyor landers photographed something that should not have existed, a faint glow, hovering just above the western horizon after sunset. Airless worlds are not supposed to have twilight. The glow appears to be sunlight, scattering off a low, thin haze of dust particles a few millionths of a meter across, floating near the surface at the day-night line. Apollo astronauts saw something similar from orbit. Crews on Apollo 8, 10, 15, and 17 repeatedly observed and sketched what they called bands, streamers, or twilight rays in the seconds before lunar sunrise and sunset. And Apollo 17 left behind an instrument that recorded the strangest evidence of all. It was called LEAM, the Lunar Ejector and Meteorites, experiment designed to detect the tiny high-speed particles kicked up by micrometeoroid strikes. Instead, it registered up to hundreds of events per day, far beyond every prediction. The events surged around lunar sunrise and sunset, beginning tens of hours before the Terminator arrived. And when engineers studied the signals, they concluded the detector wasn't seeing high-speed meteor debris at all. It was being hit by slow-moving, highly electrically charged particles of ordinary moon dust drifting across the surface. The picture that has emerged, and a model proposed in 2005 by researchers at NASA's Goddard Space Flight Center, describes it is that the moon's surface behaves like a vast electrostatic machine. On the day side, harsh solar ultraviolet and X-ray radiation knocks electrons out of the dust, charging it positive. On the night side, solar wind electrons charge it negative. The finest grains repel from the surface and loft upward anywhere from meters to kilometers high, then fall back, over and over, like a fountain frozen in place. At the Terminator, where day meets night, the electrical stresses may be strongest of all. If this is right, then the stillness of the moon is partly an illusion. The surface is dusted by an almost invisible, constantly stirring veil of charged grains. And over decades, some of that veil settles on everything, including, perhaps, a small panel of 100 glass prisms in the Sea of Tranquility. To be clear about what we know and what we suspect, the dimming of the reflectors is a confirmed, measured fact. Dust or abrasion on the prisms is a hypothesis, the leading one, but a hypothesis. The researchers who discovered the deficit say these mechanisms can be tested in laboratory simulations and must be understood before we design the next generation of equipment bound for the lunar surface. Either way, the implication is quietly profound. The lunar environment damages optical equipment on the timescale of decades. The moon is not merely preserving what we left there. Slowly, patiently, grain by grain, it is burying it. To appreciate how strange all of this is, it helps to step back and compare. On Earth, the physical traces of an event like Apollo 11 would be gone almost immediately. A footprint on a windy plane lasts hours. Fabric left outdoors lasts a few years. Even great structures erode, oxidize, get overgrown, get scavenged. Our planet actively erases its own history. The moon does the opposite. 50 years on, the Lunar Reconnaissance Orbiter's cameras continue to image the Apollo landing sites whenever possible, under multiple lighting conditions, and the scenes are essentially intact landers, instruments, rover tracks, and the darkened trails of boot prints, all delicately preserved. As a team of lunar scientists put it while marking the 50th anniversary of the final landing, the sites, the hardware, and the footsteps remain. In a very real sense, these are the best preserved archaeological sites in existence. They simply happen to be on another world. And the ledger of change we've assembled is remarkably short. One flag knocked flat by rocket exhaust, its siblings bleached white, optical surfaces dimming under a suspected film of dust, a surface being reworked by micrometeorites on timescales too long for any camera to notice. That's it. That is 57 years of history at Tranquility Base. Now compare that to what sits in the neighborhood. Roughly 400 kilometers northeast of the Apollo 11 site, in the same dark plane, there is a hole in the moon. It's called the Mare Tranquillitatis Pit, a nearly circular opening about 100 meters across and around 105 meters deep, with walls that drop vertically into shadow. It was first spotted in 2009 by the cameras of Japan's Selene orbiter, and it is the deepest lunar pit known. More than 200 pits like it have now been found across the moon, places where the surface has collapsed into some void below. For years, scientists suspected those voids were lava tubes, hollow tunnels left behind billions of years ago when rivers of molten rock crusted over, drained out, and went cold. Then, in 2024, a research team led by Leonardo Carrere and Lorenzo Bruzone at the University of Trento reanalyzed radar data that the Lunar Reconnaissance Orbiter had collected back in 2010 when its radar instrument pinged down into the pit. Published in the journal Nature Astronomy, their analysis found reflections coming from underground evidence of a cave conduit leading away from the pit floor. The entrance appears to be at least 45 meters wide, extending somewhere between 30 and 80 meters, reaching as deep as 135 to 175 meters below the surface. As Kara put it, they had found a sort of front door to enter the lunar subsurface, and here's why that matters to our story. Everything we've seen happen to the Apollo hardware. The bleaching, the radiation, the temperature swings, the slow rain of micrometeorites, the creeping dust, none of it reaches down there. A thermal study in 2022 concluded that the pit stays around 100 degrees warmer than the surface during the frigid lunar night and about 20 degrees cooler during the day. Inside a cave, rocks sit pristine, shielded from the solar wind and cosmic rays that have weathered the surface for eons. Researchers now regard the pit as a promising site for a future lunar base natural shelter, ready-made for the humans who eventually return. So the comparison writes itself. The first time we went to the moon, we stood on the surface, fully exposed for 22 hours and left our equipment to be slowly sandblasted by the sky and buried by electric dust. The next time we go to stay, we may live underground in shelters the moon carved for itself 3.5 billion years before we arrived. So, what does the Apollo 11 site look like today through a telescope? Through every telescope on Earth, and through Hubble itself, nothing. A point of grey light on a grey plane, holding its secret perfectly. That will not change until someone builds a mirror hundreds of meters wide, And perhaps, not even then, through the camera of a spacecraft skimming 50 kilometers above the surface. A small machine and its long shadow ringed by the wandering dark trails of two people who had, at that moment, traveled farther from home than anyone in history. And through the oldest instrument of all patient measurement over decades, something no photograph could ever show. A sight that looks frozen but isn't, colors quietly draining to white, glass prisms slowly dimming under a veil we can't see. A world that seems perfectly still and is instead merely slow-moving at the pace of centuries, indifferent to whether anyone is watching. Here is what we know for certain. The descent stage of the Eagle is still standing in the Sea of Tranquility. The boot prints are still there. We have photographed the trails they form. The reflector still answers when we call. And here is what we don't know. How long the prints will last against the patient rain of micrometeorites. What the flag looks like now, lying face down after half a century of unfiltered sun. Whether it is truly dust dimming the reflectors, and if it is, how a world without wind keeps managing to move it. Every answer brings another question. That's how science moves forward. And that may be the most fitting monument of all. The first place humans ever touched another world is still teaching us, still surprising us, still refusing to be fully known. Two men spent 22 hours there. Then they left, and the moon closed over the silence behind them. We cannot see the footprints. We cannot visit them. So every clear night, from a mountaintop in New Mexico, we send a beam of light across 380,000 kilometers of darkness just to touch something we left behind and wait, in the quiet, for a few faint photons to find their way home.